In the early 18th century, researchers lacked a steady, reliable supply of electricity. They were restricted to static, energy that could be generated by friction, but never made to flow in a continuous stream. To store this charge, scientists used the Leyden jar. This glass vessel was essentially an early capacitor, capable of holding energy, but only releasing it in a single, instantaneous shock. It was a container, not a generator. The search for a more sustainable source eventually shifted from the physics lab to the anatomy table. In the 1780s, Luigi Galvani began a series of experiments involving the dissection of frogs near electrostatic machines. Galvani observed a curious phenomenon. When a metal scalpel touched an exposed nerve, the dead frog's leg violently kicked as if it were still alive. After extensive testing, Galvani concluded that he had found a new form of energy. He termed it animal electricity, believing that living tissue naturally generated and stored this vital force within the muscles and nerves. This biological theory gained massive popularity, yet it inadvertently stalled progress for years. By focusing on a mysterious life force, scientists ignored the metallic interactions happening right in front of them. Alessandro Volta was initially a supporter of Galvani, but his skepticism grew. As he repeated the experiments, he suspected the frog wasn't a power source, but a wet, conductive detector. Volta deduced that the electricity was actually generated by the contact between two different metals, like a steel blade and a brass hook, bridged by the moisture of the frog's flesh. He bypassed biology, stacking alternating discs of zinc and copper, separated by saltwater-soaked cardboard, creating the voltaic pile. Zinc oxidizes and dissolves, shedding electrons into the circuit. At the copper layer, hydrogen ions catch these incoming electrons, completing the circuit and maintaining steady flow. For the first time, electricity was no longer a momentary spark or a biological mystery. It was a sustained current produced by the controlled chemical decay of metal. Despite its success, the voltaic pile carried a mechanical paradox that limited its lifespan to minutes. It suffered from an internal suffocating effect called polarization. The first problem was structural. To produce electricity, the zinc anode must literally dissolve into the acid, wasting away its own power source to function. The second problem was gas buildup. Hydrogen ions at the copper plate turn into hydrogen gas, forming a physical barrier of bubbles. As an insulator, this layer creates an opposing pressure that chokes off electron flow. Within an hour, the battery is dead. The very reactions required to start the river of power were the same ones that eventually dammed it. Sustaining that flow would require a way to keep these volatile chemicals apart. Fixing polarization required an engineering solution that could physically isolate the reactions so they couldn't interfere with one another. In 1836, John Frederick Daniell used two separate electrolytes. Placing zinc and copper in their own containers prevented the reactions from poisoning one another. A porous ceramic spacer then allowed ions to migrate, maintaining the circuit while preventing insulating hydrogen bubbles on the copper. This stability allowed electricity to finally leave the laboratory. For the first time, a level voltage could be maintained long enough to power the world's first long-distance telegraph networks. By abandoning the theory of animal electricity and forcing metals to carefully consume themselves, Volta and Daniell turned a wild spark into a reliable, continuous flow. In doing so, they provided the literal circuitry for the modern electrical grid.